All right, you guys, this is Unit 5. We're looking at video notes first and segment 1, space. This, by the way, the video notes are to be done after we've discussed this in class. And if you have been absent, you'll definitely be wanting to do these notes. I'm going to recommend that you do Cornell notes when you watch these. This is where you will take a sheet of paper and you'll draw a line just as these lines are drawn. In this main body of your sheet, you're going to include keywords and ideas, vocabulary words, things that I have written pretty much on the slide. Diagrams, all of that goes in the big portion. And then after you've taken these notes, it's really good to go back through and come up with a key question. So after the notes are done, write a key question there that will allow you to flip back through these notes very quickly later on when you're studying them. And then summarizing your notes down at the bottom is really helpful for you to rehash through the content that was presented in this segment. Okay, I'm going to try to move fast because I have 15 minutes here. So segment 1, driving questions. These are the ones that you were given at the start of the unit. For segment 1, we're looking at how are elements made and how does the sun provide the energy the earth absorbs and reflects. So where does our earth get its energy from? I mean, ultimately, 99.9% of the energy on our planet really is coming from the sun, streaming across space. Okay, where does the sun get its energy from? Ultimately, the core area, the very center of the stars, that's where the pressure and the temperature is going to be the most intense. So fusion occurs only in that core area. With the process of fusion, this is a nuclear reaction. So with the process of fusion, you've got energy being delivered. Big energy. Fusion is a very, very powerful process. And the stars, they're not combusting, they're not burning. They're actually going through a nuclear reaction. The nucleus of atoms are actually being shoved together. It's pretty intense. So nuclear fusion is also called nucleosynthesis. Nucleo, looking at nucleus of the atom. Synthesis is the making, so it's creating a new nucleus, a new elements, the combining of the nuclei from lighter elements and forming heavier elements. I'm going to revisit, you guys in the class, you're going to be looking at the periodic table of elements and understanding, the difference between one element and another is really a proton. A matter of the number of protons. So the lightest element there possibly is hydrogen. So if light elements are going to combine, fuse together, push together to actually form heavier elements, we really have to start the story with hydrogen. Hydrogen is the lightest. It has 1 proton. Guys, the nucleus of atoms consists of proton and neutrons. You learned that in chemistry. So neutrons do not have an overall charge, but protons have a positive. And we're talking about fusion. We're talking about slamming together of two or more nuclei. Well, that's protons. Protons are positive. Positives want to repel. So what the heck, Mrs. Poulsen? How is this possible? And the answer to how is this possible is the intense temperature and pressures we're talking about inside the stars. They are incredible, unlike anything we could ever imagine on this planet. So the top elements that are found in stars really are hydrogen and helium. And there's trace amounts of others, but primarily we're looking at hydrogen. Why? Because most of the universe is made of hydrogen. We'll talk more about that later with the Big Bang. But hydrogen is where the story starts. So hydrogen fused to actually make helium in the core of stable stars. Hydrogen fusion requires a few things, excessive heat and high pressures to overcome the repulsion of the positive protons. So this high heat and this high pressure allow for very fast atomic motion. I mean, these protons, they are moving really fast when they're slamming into each other and forming a new nucleus. The heavier their element, the more heat and pressure is required to actually fuse nuclei. So hydrogen fuse into helium, but helium won't fuse into anything heavier until the pressure and the temperature become even higher. So heavier elements require this because they have more protons, which means more repulsion. So you have to have more heat and more pressure to overcome this additional proton and its repulsion. At these temperatures that we're talking about in stars, we're looking at elements not in the form of a solid, liquid, or a gas, but instead of a plasma. Plasma is the fourth state of matter, and it just consists of charged particles. If you take a peek at these diagrams, they're kind of showing you, and we'll talk about these diagrams in class, but I wanted to include them in here. Specifically in the sun, you're going to find the highest pressure and the heat only in the core area. And that's why fusion is only really occurring in the core. Sometimes, when I was younger, I thought fusion all over the place, it must be happening all over the place. No, it actually is only happening in the very center. And that's where your heat and your pressure is going to be the highest. But nuclear fusion is a nuclear reaction, and it will release a lot of energy, a lot. Einstein came up with the equation E = mc squared. You may have heard of that before. E is energy, m is mass, c is the speed of light. So mass, moving the speed of light squared, is actually going to be converted into energy. Is that wild? So this illustration I showed you in class is showing you've got 4 protons, 4 hydrogens fusing to make 1 helium. Well, the mass, that means less mass. How can 4 protons make 1 helium? If you look at helium on the periodic table of elements, it only has 2 protons. So how can 4 protons make only 2? And the answer is that some of that mass in the form of the protons is actually released as energy. So Einstein's brilliance showed us how the equation for fusion, ultimately, that's what that is. So what is the energy that's being released? Gamma radiation comes off of nuclear reactions. So we're going to talk more about that in a little bit. But fusion ultimately makes heavier elements, and it releases something called electromagnetic radiation, which includes gamma, light, UV, infrared, all of those things. So I would like you to pause this video and draw this if you didn't already in class. But these are the electromagnetic radiation examples. You start all the way in low energy with radio waves all the way to high energy gamma, and in between you have these. They only differ from each other by the wavelength and frequency. So otherwise they are the exact same. They're transverse wave that can travel through empty space. So I'd like you to write down the definition here. Electromagnetic radiation spectrum. This varies by wavelength or frequency from high energy gamma to low energy radio. Write down all these this information about this radiation because we're going to build our understanding of stars from it. So they all can travel the speed of light. They all can travel through empty vacuum. So the vacuum of space, we're able to see the stars because light can travel through empty space, right? They're all transverse waves, and stars will emit all of these wavelengths, but they actually peak or put out more in certain wavelengths. Specifically in the sun, you're going to find the highest pressure and the heat only in the core, which is what we mentioned. That's why fusion only occurs there. Oh, I already showed you that. Okay. Primarily with fusion, 100% of gamma radiation is coming out of that core. Most of the radiation from the surface, though, that's coming off the surface of our sun, for example, is in the form of light. So in this graph that you looked at in class, you see it peaks in the light frequency, so visible light. But we can see here that some ultraviolet radiation is coming off, and some infrared radiation is coming off. So something happened between the time it was coming off of the fusion reaction as gamma for it to become lower forms of energy in the form of visible light. So as it travels through, it is converted into lower forms. So that must mean that there's some layers, there's some material that it's traveling through. So the anatomy of the sun tells us there's got to be more to it. There's got to be something more. And we've noticed with the fusion happening just in the core, it's got to radiate out, and then it's going to be entering into some charged particles in the form of plasma. So it actually convects, like bubbling, like boiling water almost. So if you didn't already draw this in class, you should draw this in your notes. This is the anatomy of a star. We know that there's a core area. There's a radiative zone that is primarily radiation coming off of that. Primarily it's gamma. As the gamma radiation moves through this convection zone, it is converted into lower forms of energy. It then hits the photosphere, which is the actual surface of the sun. That's what you actually see when you look at the sun. And then it moves through the atmospheric layers called the chromosphere and the corona. We do have some features, prominences, and sunspots are shown on this in this illustration too, and you should include those as well. You'll need to know them. So again, if you didn't draw this during class, you should draw it now. The forces being fusion outward, gravity inward. These forces are balanced with a stable star like our sun. Once fusion stops, the engine stops, gravity will win and will implode the core, ultimately resulting in. So even though the sun doesn't explode, the sun does stream out solar wind, which is charged particles, and they're highly energized, and they just stream off the surface all the time in all directions. Energy travels the speed of light. The energy that's coming off of the sun is traveling the speed of light, and it takes 8 minutes to reach the Earth. But particles are going to travel much slower, and the plasma, the solar wind that's streaming across, actually takes 3 days. So we can see the prominence, the release of energy, before we actually feel it, before we get onslaught. A rule: when the sun features such as solar prominences, CMEs, and solar flares and sunspots occur, an increase of solar wind is released. So when you see those features, that means that the sun is active and releasing. Early in class, we drew this magnetic field image. Solar wind that's coming across from space from the sun will actually come across, hit the magnetic field lines, and travel along it. This is where it enters. These are magnetic field lines, these blue circles around the Earth. So when the solar wind comes in, it creates these amazing auroras because it excites the atoms in our upper atmosphere, and those atoms, those electrons, will start jumping orbital paths, and it will release light in response to that. So there's some really awesome auroras that occur. And auroras are defined as a display of light and color in the upper atmosphere caused by the solar wind. These are amazing. Sunspots, though, there is a sun cycle, and these are sunspots that you can see on the surface of the sun, which we talked about in class, but they show an increase in radiation coming across. That's indicating activity. They're actually areas of cooler temperature, but the presence of them shows that the sun is very active, and sunspots peak every 11 years. And that is it. That's where segment 1 is done.